Let S be the subset of R2 consisting of all points x, y in the unit square for which x or y or both are irrational. With respect to the standard topology on R2, S is closed, open, connected, totally disconnected, or compact. Wow, okay. Well, it's not closed, right? The definition of closed is it's the complement of open. And this I mean, what does the complement of this set look like? Is it a set of all rational? So if one is irrational, it's in this set. Yeah, so the complement of S is Q cross Q, restricted to 0, 1, of course, which is not open. So A is wrong. B is also wrong. Oops. I mean, if we're in the standard topology on R2, if I put a ball around any point, B, X, Y, this will contain points in here. So it's not open. Connected. Okay, so it's not compact because it's not sequentially compact. You know, you can easily find a sequence that converges to 0, 0. Right? It's easy to find xn, yn in this set S. So just choose where xn and yn are both irrational and both go to 0. But it can converge to 0, which is not in S. So the answer is not E. C and D, connected. So I admit I forget the definition of totally disconnected. Don't remember it at all. In fact, even what does it mean to be connected? Connected is if you write it as the union, the disjoint union of two sets, they cannot both be open. Well, hold on, that's not exactly, is it? Hold on. So to talk about connected, you have to inherit a topology. I'm going to very quickly look up the definition of totally disconnected. Because maybe like again, I've completely forgotten what the definition of totally disconnected is. And maybe it's immediate from its definition that this is the correct answer. Topological space is totally disconnected if the connected components in X are the one-point sets. So topological space is totally... Okay, I need, again, the proper definition of connected component, which goes to connected space. Okay. So a set is disconnected if it is the union of two disjoint, non-empty open sets. I knew that. Huh. I think it's connected. I'm going to put check question mark here. Can I find two open sets? No, I think I mean, if you can, they're certainly not going to be nice, right? If I have like two open... So an open set in the inherited topology if I have two open sets disjoint in the topology that S inherits from R2, then those must come from two open sets of R2. And so but wouldn't that even imply that well, it wouldn't quite imply that R2 is disconnected, because I think it might. I mean, I'm pretty sure the answer, I'm like extremely certain that the answer is C. Totally disconnected means the only connected components are singletons. But if I take a singleton and put an arbitrarily small ball around it, I hit another one of the points. Is that a contradiction to totally disconnected? Probably. In fact, that's got to be it right there, right? If this set were totally disconnected, then it's a union of all of its singletons, and but I should never be able to put a ball around a singleton and hit another point. But I do, because there are always more points in there. Yeah, I mean, I'm going to say C. I hope I've remembered enough of this stuff that that I haven't made any silly errors here. And it was nice to refresh my memory on what totally disconnected means. It's a pretty simple definition, actually. Yeah, I'm sorry I don't exactly have the best explanation for this. It would, I suppose, take like quite a bit of time to work out. I think one way to do it though is like if S were not connected, then you can probably, then you should be able to show that the unit square is not connected, but it is. That's probably like the proper argument for all of this. But I'm not going to work out the details. Yeah, I'll leave it at this. I'll say C, but if that's not correct, then I will make a comment somewhere in the video. Thanks for watching.